And did you pray?
Yes.
Okay, I forgot already. Oh no, this is going to be a bad class. Alright, you push record. Alright, Hannah, my apologies are on the overhead, and that doesn't tend to show up well on these videos, but you can listen to what I'm saying and eventually get this handout, or not really a handout, these notes from someone. Maybe pair it up, then it's up to you. Alright, we're giving it a try though. Thank you. Alright, on Friday we introduced the new mod, so that's why you're in new seats. And, oh yeah, this isn't just for you, Hannah, it's also Alex and Jonathan, so. Alright.
Hello, people.
Yeah, everyone say hello.
We miss you very much.
Yeah, we're having a hard time going forward without you.
Lucky schmucky.
We had discussed that this whole mod is going to be dynamic rotational equilibrium, but we decided we no longer wanted to call it that. So, what is the simpler, easily understood title that we gave to this mod? You can look if you forgot. Looky, looky.
In your bookie.
Did you get it?
Uniform
Where's your
circular
notes
motion.
from last time?
I left my physics thing at home.
Uniform circular motion.
Uniform circular motion. So, I have a sample of it here. I can turn the light on for our viewers' sake. That's a neat little gizmo there. Alright. Uniform circular motion. Here it is. What is different about this? This is uniform circular motion. This isn't. Alright, what's the difference? Why is this
One is constant.
right? Constant velocity, right? So uniform circular motion has a constant velocity. So, are you getting hypnotized? Around and around it goes. Alright, I need you to stay awake, so I'll stop. Alright. Does it help any better with the video if I leave the lights on?
Not at all.
Still
It's actually
show
better
up?
with it off.
Alright. Alright. Turn to your comp book where we made that note. That's about all we said the other day. Alright, dynamic rotational equilibrium is renamed uniform circular motion. That's what we're studying today. Alright, here's a picture of it. That doesn't show up. Amazing. I don't know why. It's so dark on the board there. Is it something to do with the screen? What about if I put it on the board? All these methods.
Oh, I can see that. I can see that.
Are you kidding?
No, that comes
Can
up
you guys
completely
see
clearly.
it? Alright, we're going to switch to that. It's not as good for you because it has Oyos in the middle of it. Why don't we go ahead and take this down. Our assignment for tonight, I'll just do a little aside here, is written there so I can erase it. Oyos, when you finish this lecture, hopefully well before the end of class, so you can actually do these in class, are Oyos 7, 1, 2, 3, and 4. And then you have 2 pages, parts of 3 pages to read. I think 228, it starts at the bottom, and 230 ends at the top. So you've got a little more than 1 page to read and take notes on. So that's your assignment. Remember, we don't meet on Tuesdays, so that'll be for Wednesday, but remember that we do have it, that assignment. I'll erase that so it's not bothering my video. Everyone got it? Dynamic rotational equilibrium has been renamed to uniform circular motion. My question for you, because it is rotating in a direction with constant velocity, is the acceleration 0? I'll give you a clue. I'm setting you up for failure. Is the acceleration 0?
Yes.
You failed. All right. I set you up to fail because we have learned so far in the past wherever acceleration, I mean where velocity is constant, that acceleration is 0. But in this case, we have to recall that now that it's going into a circle, acceleration is a vector. We knew that from the past. That's a real blast from the past, which involves magnitude, which is a number, and direction. One of these, direction, magnitude and direction, every vector has two parts. The magnitude is not changing, and the acceleration of the magnitude of this vector is not changing, so it is 0. But the direction changes constantly when you're going around in a circle. So that's why we have to say that acceleration is non-zero, because the direction is changing. So there's a little tweak there in our understanding of constant velocity and acceleration. All right, on Friday, we drew a circle and we put in the 4 velocity vectors. So when I'm spinning this around, like this, if I was to cut it right when it hit the top there, you have to realize what way the velocity would take. And that's the velocity vectors. You're going to pick 4 spots on the circle and draw in the velocity vectors. We did this on Friday, so see if you can recall how it works. Pick 4 spots. I did my monkey math spots for those who had me for that. For those who haven't, you have yet to learn about monkey math. So here, I think you recall that, like at the top, if it was going this way, maybe you're drawing yours going the other way. Doesn't matter. But if the velocity in around the circle is counterclockwise like mine, they will zing off in that direction. If you're going the other way clockwise, they'll zing off in the other direction. But in straight lines tangent to the circle. So, did you draw in your 4 vectors? Mark them with a V for velocity. Alright, then, let me move this up. I want you to add the acceleration vectors. Acceleration we talked about on Friday as well. So you're just redrawing what we did on Friday. Add the acceleration vectors. Who remembers which direction? This it was hard to visualize. I had to teach you that. So Abby, which way?
Isn't it towards the systems?
Yes. So acceleration at each spot will go toward the center. And you put an A next to those. And mine's going to get crowded. Hopefully yours is a little larger than mine. For those who are looking on video, I just added little A's here. It's for acceleration. And lastly, because force and acceleration are so connected by Newton's second law, we learned that force is going to mimic acceleration, only is it going to be longer or shorter. You recall how that works?
Longer.
Right, it is longer. So we want to add the acceleration vectors. They're going to be, the force vectors are going to be longer than the acceleration vectors. And I just put 1 in because it got too crowded. But you can go ahead maybe on your paper and put all 4 force vectors in. There aren't just 4. There's an infinite number. So you added the acceleration vectors and the force vectors. And there's one question up there I haven't answered, and that is what I introduced on Friday. What force causes acceleration when it's in a circle like that? So I want to add the word circular acceleration. Morgan?
Centripetal.
Centripetal. What about when I write on? Does that show up, Molly, when I write on the board like
Yes.
that? Does it? Awesome. All right. So that took us to where we were on Friday. So we're ready to
The time
plow
is finished.
some fresh what?